So,
and then we need a PowerPoint back screen. All right. Welcome to the follow-up stream number 1 week into the hackathon.
Yeah.
Yeah. So
our clicker is out of function. So if we can click manually.
Okay. My name is Magnus Sandevong. I'm working as business consultant at Stratiteq.
And my name is Goran Vukšić. I work as a technical manager for Stratiteq.
And sorry for the delay due to technical issues here. Goran, I will arrange a hackathon next time, which is about building smooth softwares for going online and having live sessions and so on.
Way too many cameras and cables and buttons to click, but so it's normal.
Before we go into the list of the partners for this hackathon, let me ask you, we are 1 week into the hackathon. What's your reactions or reflections so far?
Yeah, I think it's interesting. Like teams had a lot of questions to mentors. There was a lot of direct communication going on, and there was a lot of interest in the challenges, in the data and such. So yeah, I believe they are figuring the right solutions now, and that they will push in the next 2 weeks to make some amazing presentations and demos for their ideas.
The first days the mentor showed up based on their committed time, like this. Hello, I'm mentor 1, I'm here. Hello, I'm mentor 2, I'm here. And it was not so many conversations at that time, but now it has increased. And I've seen that you are there 24 hours a day.
Well, I need to sleep sometimes, but I'm trying to be there and answer the question. We got the comment that sound is doubled. For some reason, if we can maybe check that.
Yeah, I'm a stalker at Discord. And when my youngest daughter heard us talking about Discord over an online meeting, she said to me afterwards, "Dad, are you at Discord? That's a gaming conversation platform." So maybe she will log out now and delete her account.
No, it's the thing is, it started as a gaming, but it's really used in many different areas. And like all those online tools previous year, from obviously reasons, got the boosts, and people use them more.
Mm-hmm.
So, yeah.
Cool. Can we have a next slide, please? So,
yeah, for healthcare hackathon, this hackathon takes place online for 3 weeks. We have 1 day per week on Wednesday, this touch base with all the teams, and mentors are available from 10 a.m. to 2 p.m. to answer your questions. Also, you've seen a lot of mentor activity during the week. They really try to answer your question outside of this dedicated time, which was great. So during these 3 weeks, teams are trying to solve challenges from leading hospitals across Europe. They will submit the challenges. Hackathon Council will pre-select the best ones, and Hackathon jury will vote. And we will have some winners. And after the hackathon, there is a lot of interesting prizes that we have so we will mention that today.
Yeah. So let's have a look at the organizers behind this hackathon. We are proud to say that we are in partnership with Microsoft for the second time to arrange a hackathon like this. And we as Stratiteq are hosting and organizing the event as well. So when it comes to the other main partners, they are three. We have Nvidia, which is well known for most of you probably, and I can tell you that today's guest is Rob Brisk from the Nvidia. We have SAS, and we have Women in AI. And when it comes to the company's organization and so on that brought challenges to the hackathon and is partnering with us in some way, they are Foundation 29, HM Hospitals San Rafael, Sanitas, and University Hospitals in Basel.
We also have supporting organizations, and those are Live AI, Microsoft for Startups, Microsoft Reactor, Faculty of Organizations and Informatics Croatia, Hackathons Australia, Global AI Student Conference. So, important information. You already know that Hackathon is running on the platform called DevPost. Hopefully your team is now registered there, and all team members also. We have our main communication tool, Discord, where you can communicate with organizing team, with mentors, and you can also communicate with other teams to discuss how they approach challenges, maybe. Deadline to create project page on DevPost is today, which means that today you need to go to DevPost, create project page, write which challenge and track you work on, and over there, like when you create project page, you need to go through all four steps in creating project. So all 4 steps need to get a check mark there. Some fields are required, like YouTube video, for example, or any other video. You can put a dummy link for there and dummy text, like if it's required. But we need to know today teams there and which challenge and track they work on. Also, one of those steps is to add your team members. So send them invite, check are they added over there. If you have any issue with creating the project page, or you want to validate are we able to see it, feel free to reach out directly via Discord. We will check is everything there and let you know you are good. So,
what about the data sets? Lots of discussions is about the data sets in Discord.
Yeah.
Availability and access and so on.
Yeah, mentors are available today from 10 to 2 again. For sure, that is the dedicated time. So feel free to reach out and have a chat with them, and yeah, ask them to explain you data if it's not clear immediately or stuff like that.
Okay.
So please do so. Yeah, we will touch base again via the live stream, and mentors will be there next week on Wednesday also. So we have these weekly follow-ups, right? And in 2 weeks, your project should be submitted until 6 p.m. Winner announcement will be on May 21st. So then we have another live stream. Moving on to Discord, you already got familiar with that. We have text channels, we have voice channels. Text channels, general, post all kind of questions, information there, general information. We are posting there, letting you know what's happening. Challenges, ask questions there. Introduction, feel free to introduce yourself. This is great opportunity to connect with mentors, with other participants. Post your LinkedIn link over there. Let us know who you are and connect with others. looking for a team, there will not be much activity anymore there. Teams are formed. Mentors, you ask questions over there. Selfie, please post your pictures there. We would like to see your team. Maybe take some picture when you have video conference, so post it there. Voice channels, you can invite mentors to discuss topics with them on these voice channels. We have a general channel where today we will organize one virtual coffee. We will grab a coffee and connect there. We will let you know we are online, so feel free to join us and have a quick chat. And yeah, meeting rooms, join there with mentors.
And the first selfie out was yesterday. There was a cat showing up.
Yeah.
Have you seen it?
That was cool. That was from Florian. He's from Microsoft Switzerland.
I don't know the name of the cat, but he said it was programming. So.
Yeah.
All right, let's have a look at the challenges. We have 3 tracks where you are developing solutions within. First, we have the AI applied to the medical imaging. We have the predictive medicine, and we have the empower patients. So, anything more to say about the submission criteria, Goran?
Yes, submission criteria is that you have video presentation not longer than 7 minutes. No one has time to watch 1 hour explanation. You should be able to explain it in 7 minutes. On previous hackathons we had 3 and 5. 7 is, since this is a complicated topic, I believe enough time to show demo quickly, to explain what it is about, and to show the team behind it, because team is super important. And all other description can be written on the page, DevPost page, where you can include different links to data sources, to science papers. You can include pictures, explain how it works, some architecture. Whatever is relevant, you can put in the page description. So the way the council will review the projects and the way the judges will vote, they will look at the video, and after watching the video, they will go through text to find additional information about it. So use this page. You already have a template there. You can use like what you accomplished, how it works, which technologies were used, and such. You can describe the project based on this template, but you can also modify the template and make it, adjust it however you like it. So it's not a must that you need to follow this template. So video presentation not longer than 7 minutes, and project description.
So for pop songs, they're saying 3 minutes, but for pitches within the hackathon, they are saying 7 minutes. Okay, let's have a look at the judging criteria. The council and the judges will look at 4 parameters when they are evaluating the solutions. First of all, it's about the impact. What kind of impact would the solution have in the reality if it's going to be implemented? The second one is the feasibility. How realistic is it to implement a solution when it comes to technical things, legal things, and other practical considerations? We have the third one, which is implementation. How long has you as a team come when it comes to bring up the solution itself or the software itself during the hackathon? And the last one is about innovation. In what way is the solution innovative and creative, and are the latest technology used or not? So that's what we are fighting for right now.
Okay, getting to the tasks. I already mentioned some, but it's good to repeat, because then it happens. On DevPost platform, create project page, add team members, write in the description which challenge and track you work on. Deadline is today, so that needs to be in place today. There was a question now on Discord, like, do you need to submit? Yes, you do. So you need to go through all 4 steps. When you click submit, your project becomes visible to us, and that's important, that we know which teams are there and which tracks, challenges they work on. And this submission, you can edit all the way to the end of the hackathon until it's the deadline for the final submission, 2 weeks for now, 6 p.m. And this project gallery is hidden. Other teams will not see what you work on, so it's only for you and us to be able to see that everything's in place. Discord, reach out to mentors today between 10 and 2. Try to use this time, book time with them, ask them questions, figure out like, are you on the right track, how to shape this solution better, how to make your presentation better. Maybe you have a great idea and need to shape some slides and such. You can also ask that. Keep in mind the judging criteria that Magnus just mentioned. So next live stream is next Wednesday, May 5th.
So a hackathon is nearly nothing without the prizes. So of course we have prizes within this hackathon. There will be one prize each track, so we will award a track winner. And I would say, related to this one, that there is really great opportunities within these prizes, though there will be possibilities to work together with hospitals and organizations for a couple of months to continue the development of the solution. And there will also be support from different startup organizations to evaluate the potential for the solution going forward. So there will be partner prizes as well from different kind of organizations and partners this hackathon is supported by. And if you need more information, want more information about these prizes, you can find the information at the DevPost page. So who's the guest today, Goran?
Guest today is from Nvidia. It is Rob Brisk, and yeah, he will give us some interesting information about some great accelerated medical AI toolkits that can help you iterate quickly and be more productive. So we will have Rob now on screen in a second.
Hi, Rob.
Hey.
We can see you.
Brilliant.
Yeah.
Great. Okay. I was just waiting to go live there. So thanks very much, guys. I'll do a bit of talking from here then. So I'm Rob. I'm the Healthcare Developer Relations Manager for Nvidia in Europe, also the Middle East and Africa. My background is actually in clinical medicine. So I've been a practicing doctor in the NHS for a little over 10 years. I specialize in cardiology. But I also have a computer science background, particularly, of course, focused on medical artificial intelligence. So I get to spend my time working with a range of great organizations in this space, from small startups and academic teams to huge institutions that we're partnered with, like the NHS, like GSK, like AstraZeneca. If anyone was at the GTC conference and watched our keynote, you'll have heard about some of the great work we're doing with AstraZeneca in the molecular chemistry space using transformer models. So I get to see the whole spectrum of medical AI, from the inception of great ideas that often happen at places like this, at brilliant hackathons, right up until the point of prime time production. So let me know, guys, when you can see my screen share here. It should be a web page.
Yeah, it looks great.
You can see that. Yes. Fantastic.
Yes.
Okay, so I've been following the Discord chat. I'm one of the mentors on the hackathon, and I can see that the teams are starting to pick their challenges, do some data wrangling, maybe do some early experiments. So I thought this would be a great time to talk about the fact that it's never too early to plan for success. And in healthcare AI, that means it's never too early to think about scaling. And what tends to particularly be the case is that at this very early stage, when you're a team in a hackathon or a small startup, or maybe as part of a small academic team, you're very focused on the extreme ends of what's shown here, which is a generic AI pipeline. So it's hard trying to source the data, particularly with all the data governance issues in the medical field. And you're also thinking about what kind of model architectures you're going to use, how you're going to best, meet the challenge at hand. But you tend to be limited as well by entry-level hardware. So you need to think about, well, what model architectures are going to fit in my GPU memory? What model architectures are going to allow me to iterate in a timely manner so that I don't have to spend a week at a time waiting for my model to train. What tends to happen, though, in the medical world is that as you develop a great POC, go to market, and then start selling into or having big organizations use your application, the challenges sort of flip on their head. So if you were to go out and build an application and take it to, say, a tier 1 pharma organization or a huge national health system, what you'll suddenly find is that these guys are drowning in data. I mean, you know, these big organizations, say you're in the computational pathology space, they'll have tens of thousands of digitized whole slide images to deal with. And at the other end of the AI pipeline here, they'll have high-end hardware. You know, a lot of organizations are starting to run proper AI servers like Nvidia's DGX A100 servers, which has 8 A100 GPUs per box. And these each have at least 40 gigabytes of RAM. Some of the models have 80 gigabytes of RAM. So you're dealing with blazing fast GPUs that have collectively up to 640 gigabytes of RAM per server. And your problems shift to this middle part of the pipeline. You've got loads of data, you've got blazing fast hardware. How do you keep up with training your model in a timely fashion? So you need to think about I/O, you need to think about ETL. So what's a great idea is at this early stage, when you're having brilliant ideas and you're starting to build out POCs, it's great to look for tools and frameworks that will serve you well throughout your journey, from the first iterations to prime time deployment. And there are some great tools out there. And so what I'm going to do today is just do a whistle-stop tour of some of the tools I see commonly cropping up in the medical AI space. And what I'm going to do, I'm going to walk through the different tools that I think might be applicable to the challenges in the hackathon. Goran and Magnus, can you just confirm that my window has switched to DevPost?
Yes. Yeah, looks great.
Brilliant. Okay. So challenge 1 is, or track 1 is medical imaging, which is, of course, the most mature field of medical AI, because computer vision, people talk about the ImageNet moment for AI, and computer vision rapidly translated into the medical space. So this is where a lot is happening in the medical AI space, and there's a rich ecosystem with some fantastic tools. This hackathon's got some excellent challenges. We've got a couple of challenges dealing with CT scans, so 3D volumes. We've got computational pathology in there. We've got chest x-rays in there. So there's a real nice mix of different things. What I'm going to talk about first is radiology. Radiology is a more mature field of medical AI than computational pathology, simply because it's kind of surprising to hear that that histopathology in general is still a largely manual process. Most people are still staring down microscopes at physical slides and then sticking those slides into storage as frozen sections. Digitization of pathology slides has only just started, whereas digitization of radiology studies, by which I mean CT scans, X-rays, MRI scans, that's been going on for years. So I'm going to start off by talking about our challenges that involve CT scans and X-rays. First thing I'll say, before I talk about what's on the screen in front of you, is that Python, we're sort of, NVIDIA tries to be framework and language agnostic to the greatest possible extent, but what I see personally in the medical space is Python is just hugely dominant, ever more so as time goes by. We still see people using R sometimes, but if you're starting out a project, as hopefully people are in this hackathon, I would definitely go for Python right now. I would also lead towards PyTorch. I mean, TensorFlow is a great tool, and there are some great frameworks out there like, you know, Caffe, but Torch has just really taken off recently, and again, I think PyTorch has a particularly rich ecosystem. In specifically the radiology space, check out Monai, and I will post all the links to the tools I'm going to show you in the Discord chat afterwards, but you can see them in the address bar up here. Monai is a fantastic open source Apache 2 license framework dedicated to medical imaging, although Monai is branching out to other fields of medical AI. Monai is run by a consortium comprising a range of different world-leading institutions. NVIDIA's in there, King's College London's in there, Harvard, Stanford, DKFZ, and a range of others that I won't go through an exhaustive list. So it's a great community-driven project. It's got a range of really brilliant tools and nice features that you'll definitely want to use in your radiology project. It's got built-in DICOM and nifty file format readers. By the way, just as an aside, challenge 1 of track 1 of this hackathon, you can download the studies either in TIFF format, where someone has taken the middle slice of your CT volume and transposed it into the Philips TIFF format, or you can get the files as DICOM files. I would encourage you to use DICOM, because one of the criteria we'll be looking at is implementation or feasibility of your project. If you've got a pipeline that works with DICOM, we immediately know that can be used in any clinical center. If you're limited to reading CT slices through TIFF format, I mean, ultimately there's a time component here, so do whatever you can do quickly, but think about using DICOM. So MONAI has dead easy DICOM and nifty readers. It can also handle PNG files, JPEG files, TIFF format files. It has a bunch of common transforms that you'll want to use for medical images that work not only with sort of JPEG and PNGs, but 3D imaging volumes. And you can chain those transforms together in a compose module that you'll be familiar with if you've used Torch Vision. It's got a bunch of really nice loss functions that you'll want to use in the medical imaging space. It's got a couple of performance optimization features like smart caching. So as you go through and augment your images, it will cache all the deterministic augmentations so that on the next epoch, you don't have to do the whole thing on the fly. Determinism is really important when you're thinking about medical AI. You need your experiment to be reproducible. You need it to perform in the same way every time. MONAI has a single call to set a random seed for every function in the framework that's involved in your pipeline. So it's designed with determinism thought about from the outset. It's got some really nice models that you might want to try using, like 3D UNet models. You just invoke it with a single line of code. As a lot of people might know, getting UNets to work with 3D volumes can be a bit painful. And it's got integration with a range of third-party libraries. I haven't gone through the UNet website, the MONAI website here. I would just encourage you to check it out. It's got brilliant documentations, great example notebooks. It's well worth having a look at. I'll spend probably a little bit less time on the other frameworks I'm going to talk about, but because anyone who's doing one of the radiology challenges in the hackathon, I would really encourage you to have a look at MONAI and think about building it into your stack. And I would also encourage you to think about using MONAI moving forwards. It will scale. It will serve you nicely throughout your journey. If you want some more complex image augmentation than MONAI offers a great range, but this is nothing to do with NVIDIA, by the way. I'm going to give you a range of NVIDIA and non-NVIDIA tools today. Almost all of them are going to be open source. Augmentations, if you haven't come across it, is an image augmentation toolkit. It works really nicely with PyTorch, and it allows you to be really creative with your image augmentation. If you're working with small data sets, as we all know, that can be really important. And then if you're using PyTorch and if you're using MONAI and you want a bit more functionality and you want a really super optimized pipeline because you're thinking, oh, I've got a great project here and I want this to be something that's kind of, prime time ready going to market, have a look at this NVIDIA toolkit called NVIDIA Clara Imaging. Now, this is the one thing I'm going to show today that's not completely open source. It's you can download it, you can modify it, you can do what you like with it, but you can't distribute it onwards. It's distributed under an NVIDIA EULA, end user license agreement. But that shouldn't be a problem for anyone's purposes today. This is distributed. I'll show you the next tab here. This is distributed via our NGC repository, where we keep our deep learning pre-trained models and our containers. So Clara Train SDK is distributed as a container, and it has a bunch of great features. First thing is, as with everything NVIDIA produces, Clara Train has these super optimized pipelines. So you can you set up your file, your file system in your deep learning project in a certain way. You can find this in the documentation for Clara Train. We call it the MMAR, the Medical Model Archive Repository format. So you structure your folders in a certain way. You go into a config file and you tell the config file where your different, your training files are, your validation files, your labels, and then you just run a shell script within this Clara Train Docker image, and it will do beautifully optimized training for you with distribution built in if you've got access to multiple GPUs. It's got a few nice features that you probably won't need for the hackathon today, but you might need as you move forwards on your journey in the medical AI space. It's got an AI-assisted annotation server. Now, we're seeing this becoming really popular with a range of organizations. It allows you to train a deep learning model, upload it into this server that you can run on your local infrastructure, and then using common medical imaging viewers like MITK or 3D Slicer, you can call up one of your CT volumes or one of your organization's CT volumes or MRI volumes or chest X-rays. You can upload the volume to this server that you're running on your local infrastructure, and it will send you back an annotated image or volume. It's just a really nice tool for increasing productivity if your organization does any manual image annotation, which will be the case for clinical organizations, by the way, that you'll be wanting to gear your product towards during this hackathon. Also very much the case for big pharma companies. Clara has pre-trained models built in. I will talk about one of them in a moment, so I won't dwell on that. It's also got a really nice transfer learning toolkit, a really nice federated learning toolkit, and I'm not going to talk about that at all today, but read up on federated learning. It's becoming really hot in the medical AI space. And it's also got an auto ML feature where it uses reinforcement learning to tune the hyperparameters of your deep learning model. This is really kind of cutting edge stuff. I'm not going to talk that much more about Clara Train. It is brilliant. The one reason I talked about MONAI before Clara Train is, firstly, Clara Train offers additional functionality on top of MONAI. Secondly, the current release version of Clara Train is 3.1. That's built on a TensorFlow backend. The release that's about to come out very, very soon is Clara 4.0, which is built on a PyTorch backend with MONAI integrated. So worth having a play with Clara Train during this hackathon, but the 4.0 version is going to be really one to check out. I'm still, I've switched to a different page here. I'm still on the NVIDIA's NGC repository. For a couple of the challenges, for two of the challenges in track 1 of the hackathon, you're going to be dealing with CT scans of the thorax, of the lungs. There's a pre-trained model here that we've trained to detect COVID-19 and segment out COVID-19, the lesions, the characteristic lesions you see in COVID-19 from a CT scan. The data sets, of course, that you're dealing with in any hackathon tend to be reasonably small, and you want to use all the tricks at your disposal to train your model as well as you can in a very short time space. Pre-trained models with transfer learning, of course, are a route you want to explore. There is a model available on NGC. This is freely available to download. I'll post a link into Discord afterwards. But this CT scan that's trained to annotate COVID-19, I imagine, is going to be very, very fine-tunable for the tasks you're going to be looking at, particularly, of course, the lung cancer prognostication task. Moving on then, a couple of little things I would be thinking about doing. I've had a look through the challenges. I haven't actually done any coding work because I'm mentoring, not participating. Things I would be thinking about doing in addition to transfer learning, I would be thinking about self-supervised pre-training. Of course, we're seeing this really be a huge part of the revolution in transformer-based natural language processing, but it works really nicely with medical imaging too. We just haven't seen it used quite as much in that field. In painting with medical images, where you mask out a little portion of your image and you train your neural network to paint back in, forces your network to learn lots of really useful features within your image set. And as I say, it's self-supervised, so you can pre-train your model and then you can fine-tune it using supervised learning with your actual class labels. On this Towards Data Science, this is probably a website you're all familiar with. I think it's from the Medium Corporation. There's a really nice article here that walks you through how to do adversarial in-painting with some PyTorch code. It's a really nice thing to try out. It's going to be a framework you probably want to reach for again and again as you move forwards in the medical imaging space. On that note, if you're going to go down the route of trying to do self-supervised pre-training with in-painting or one of the many other techniques you can use, you're going to need UNets. Now, none of the challenges in the hackathon are segmentation tasks, so you won't need UNets for them, but you will need UNets for self-supervised learning. UNets can sometimes be a bit challenging to work with. Here I'm showing you the docs for MONAI. So this is a 3D UNet for segmenting out, a 3D UNet for 3D volumetric studies. The other thing you can do is if you've got the CT scans of your thorax, you just break it down so that each slice of your CT scan becomes an individual training sample, in which case you only need a 2D UNet. This is a brilliant library. I use this loads. I'm actually not sure who Kubvel is, or Pavel Yakubovsky, if I'm pronouncing that name right, who wrote this, but it's a really nice, completely permissive open source licensed segmentation framework. He has a version for Keras and a version for PyTorch, and there's a load of great encoders that he's built in. So you just invoke, with a single command, you invoke a UNet, you choose your encoder architecture from all of these different cutting edge model architectures, and it pulls the pre-trained rates for you. So if you want to use one of the really big encoder architectures that, say, Facebook are using at the moment, trained on Instagram, you can just do that with a single line of code. I mean, this is a great library if you're doing anything that involves UNets in 2D imaging. That's it for radiology from me. That was probably the most I'm going to talk. I realized that was a little bit of an unbroken monologue. As I said at the outset, radiology radiology AI is a rich ecosystem with lots of great tools. So there's going to be a little bit less to talk about as we move forward through the other parts of the challenge. Now, the next challenge, I'm still on track 1 here, but I'm down to challenge 4, which is about computational pathology. computational pathology, i.e. the AI-enabled analysis of microscopy images, so usually whole slides, often of slides where you've taken biopsy specimens from tumors. This is a really growing field, and what makes it really interesting is you're not just recycling all the technology from radiology AI or indeed the wider computer vision space. Whole slide images at 40x resolution are seldom less than a gigabyte in size, and they're often much more. They are huge. And that presents a whole range of different really interesting challenges to address. How do you load these things into RAM? How do you train a model? People are generally having to use tiling approaches and weakly supervised learning, which can be quite difficult to get good results from. There's no data set that we've provided as part of this hackathon, but in the resources section of the DevPost website, you'll find a link to the Cancer Genome Atlas program. It's a resource that everyone in this space is aware of and is using. I mean, it's a fantastic, huge repository of both genomics information and histopathology slides. I actually don't know how long it takes to register this and get access to the data, but there's also a few great computational pathology data sets on Kaggle. You can just search for that. So if anyone's feeling adventurous, I realize you've probably all chosen your challenges by now, but computational pathology is a great space to be getting to grips with. What you'll find in computational pathology is that everyone is using OpenSlide. It is a library in C, but it's got a really nice Python API, and it's designed specifically to address this challenge of how do you work with massive, massive images. And it will load them up, one part of the image at a time. It will allow you to do some really nice sort of, ETL and augmentation in a way that's specifically geared up for histopathology. So you will find everyone's using this, and if you're doing the computational pathology challenge in the hackathon and you haven't been in this space before, reach for OpenSlide for sure. What you'll also find, and this is going to be, I'm moving on. This is kind of mostly relevant for computational pathology, but these are a couple of great tools that you might want to use for any sort of computer vision application. Nvidia Dali is an open source data loading library. I'll just scroll up so you can see the top of the page here. Nvidia Dali has a really nice trick that we're going to see lots and lots of people using as time goes by. Normally, when you're working with imaging data, what you'll do is you'll have your data stored in persistent storage on a disk. You'll load it up into your CPU RAM, your host memory. You'll do some augmentation and some transformations on the CPU, and you'll send it across to the GPU. And then you'll train a deep learning model with one of these frameworks. Now, this is all well and good at the early stage when your bottlenecks, as I've discussed previously, you're struggling to get hold of data and you're using low-end GPUs. But as you move into the world of industry, you'll find that actually this becomes a real challenge, particularly high-resolution CT scans, 4D scans with the time series components of cardiac MRIs or cardiac CTs, which of course we're dealing with in this hackathon, and particularly computational pathology images. Trying to load them up, transform them, and send them to GPU, what you'll find is you're sitting there with idle GPU cycles, and GPUs, high-end GPUs, like any high-end hardware, they're expensive. You don't want them sitting there doing nothing. Dali uses this great trick where it's got a really nice Python API. You can drop it in as a replacement for your current data loading functions, whether you're using OpenCV or Scikit-Image or Pillow. You drop in Dali as a replacement for that, and it will, by default settings, it will follow your existing pipeline. It'll load the data into host memory, it'll do the manipulation on the CPU, and it'll send it to the GPU. It's already highly optimized, so you probably find you get a small speed up just from invoking Dali using that standard pipeline. But when you want to move to the prime time, Dali has a feature where it will load directly from persistent storage into GPU memory. It'll bypass the CPU and the host RAM entirely, and it'll do your augmentations on the GPU. And this is with a couple of lines of code that you have to change. And you'll find you get huge speed ups from this. And so dropping Dali into your pipeline at this stage is easy. It's a really gentle on-ramp. It'll take you 20 minutes to drop Dali into your pipeline, but it will pay dividends as you scale. Dali, by the way, doesn't have a DICOM loading function. It's for standard images. So it will work with computational pathology. It will work with chest X-ray files if they're in like JPEG format or TIFF format. It won't work so well with 3D volumes in DICOM format, which is why Nvidia Rapids or Rapids QSIM now exists. Another completely open source framework. I'm just going to scroll up to the top here so you can see this is the GitHub repo I'm showing you. Rapids I will come to in a moment because this Rapids is going to be more relevant for the second track in the hackathon. QSIM stands for Q Clara Image. So Q for CUDA, Clara for Nvidia's healthcare platform Image. So QSIM like all the Rapids tools, basically takes common frameworks that you'll be used to using on the CPU, ports them to the GPU, and gives you APIs that will be super familiar. So QSIM is aiming to reproduce a lot of the cores from Scikit Image and from OpenSlide. So you can drop in. So instead of import Scikit Image, you'll import QSIM, but then from then on you'll use all the same calls to the functions. So what QSIM will do, this Git repo has only gone public in the last few weeks, so this is super new, super hot off the press. It's probably something that's worth looking at and playing with. Give it, maybe a few weeks, a couple of months before you actually start expecting full functionality from this. But it's going to allow you to do really sophisticated image manipulation. It's going to be exceptionally good for histopathology, and it's going to allow you to do that really easily. It's also going to invoke the GPU direct feature, so you can choose to load your images straight into the GPU and then do really complex manipulation. So watch this space for QSIM. And that's me off track one. As I said, track one, imaging and pathology, big space, lots of talking. I'm going to do a lot less talking, as much as anything, because predictive medicine, which is track two, is a very broad field. I have less sense of exactly what kind of pipelines people are going to be using here. But in track two, what's clear is you're going to be doing, basic data science. Well, I say basic data science. Good old-fashioned data science and machine learning are probably going to play a big part for any teams tackling challenge 2 of this hackathon. To that end, you'll be using things like probably scikit-learn. Everyone's going to be using NumPy, because who doesn't use NumPy, right? You're going to be using probably pandas. Have a look at Rapids, rapids.ai. As I said previously, this is a completely open source data science framework that basically GPU accelerates the libraries you will be used to using as part of your data science workflow. And as I've already explained with QSIM, the idea of Rapids is libraries get produced that the calls to the functions are super, super familiar. So, for example, we've got QDF here, which is CUDA data frame. It's basically a drop-in replacement for pandas. And as you can see, just from this tiny snippet of code, if you're used to using pandas, the calls will just look exactly the same. We've got QPy, which is an equivalent to NumPy. We've got QML, which is for CUDA machine learning. It's a drop-in for scikit-learn. QGraph, which might be interesting to some teams tackling this challenge, which is a drop-in replacement for NetworkX. And then, of course, I've already mentioned QSIM. You may or may not, a lot of the teams in the hackathon probably won't have access to enough GPU compute, even though Microsoft have very generously provided the Azure passes, so you will have access to some. You might find that you've not got access to high-end enough GPUs that it's worth porting your code over to GPUs at this stage. But this hackathon's all about making great connections. It's about having great ideas, and it's about learning new things. Taking away the fact that Rapids exists, and that when you're working in a setting where you do have access to serious infrastructure and you do really want to make your code run blazing fast, if people take that away, that'd be fantastic from this hackathon. That's all I have to say on the tools and tricks for the predictive medicine challenge, because it's probably the broadest one. Empowering patients, which is track 3 of the challenge, which, by the way, is super, super important. I think it's fantastic we've got a track entitled Empowering Patients. This, from a machine learning and AI perspective, it's probably going to involve some NLP, right? NLP is possibly the hottest area of AI at the moment. It's where all the amazing breakthroughs are happening. It's where we're really pushing the edge of what is possible. Anyone who's played around with GPT-3 or even seen some of the outputs of GPT-3, which of course is a 175 billion parameter transformer network, really it gives you a sense that we're taking steps towards what is eventually going to turn into what some people refer to as generalizable AI. I mean, there's spooky stuff coming out of this, and it's just amazing to see. So NLP is a great area to be in, and I wouldn't be surprised if some teams had chosen this track just to get their hands on with some of the NLP tools that are coming out at the moment. Let me show you a couple of things that are really worth thinking about in the NLP space. So NLP is becoming synonymous with transformers, rightly or wrongly. The fact is that traditional NLP approaches, things like deterministic NLP functions or even recurrent neural networks, they're just being superseded by transformers. And transformers are compute hungry to the nth degree. They're fantastic in that they're pushing the cutting edge and they're exciting. There's a challenge in that most data scientists don't have access to the compute they need to train their own transformers. So what we're beginning to see is frameworks that allow you to really make the best possible use of the compute you do have, but also, if you do get access to more compute, will allow you to scale to a multi-node setting. And really, if you're going to be doing serious work transformers, you do want to at least be using multi-GPU and often multi-node. The Nvidia Megatron language model library is really taking off in this space. And I will talk in a moment about how Nvidia and Microsoft are really in sync in this space. It's, again, completely open source framework. It basically abstracts a lot of the painful steps you need to take if you want to work with transformers, particularly if you want to work with transformers in a multi-node setting. I won't talk about it too much, but if you're thinking about picking up transformers for NLP as part of this challenge, have a look at Megatron, go through the documents, get a feel for it. The thing we're finding slightly challenging for people who already have pipelines is a lot of the different transformer pipelines. You know, some people like PyTorch Lightning, some people like vanilla PyTorch, some people go for Megatron. The different frameworks don't always play terribly well with each other. I'm not just saying this because I'm employed by Nvidia. If I was starting an NLP project from scratch right now, I would be working with Megatron, partly because it's a fantastic framework, but partly because of the Microsoft tools that are really in step with Megatron that are allowing you to push the cutting edge, and I will talk about them in a moment. Just to point out that there is, Nvidia has trained a 345 million parameter, what's the word I'm looking for? It's not a clinical, it's sort of a preclinical language model, which we call Biomegatron. So Megatron is Nvidia's language framework, named, of course, because it's meant to deal with transformers. But Biomegatron is the biological language model. It's in the preclinical space rather than the clinical space, so it may not be relevant to track 3 of this hackathon, but it's worth knowing about. It's completely open source as a model checkpoint, and here you can find, I'm now on the Nemo repository, which is another open source NVIDIA framework. Here you can find just a really nice workbook that walks you through how you might want to use the Biomegatron language model checkpoint to do something in the preclinical NLP space. Again, links will be in Discord afterwards. Now, this is one of the reasons that I would be reaching for Megatron language model framework if I was doing any project that involves transformers right now. Not just because Megatron itself is a great framework, but also because DeepSpeed, which is a Microsoft framework, is integrated beautifully with Megatron. They just work hand in hand. Like, you have PyTorch underneath, and then you have Megatron and DeepSpeed on top of that. And we're using these frameworks to scale transformer models over like 20 plus super high power nodes on our massive supercomputer systems, and it really can achieve amazing things. DeepSpeed, I have looked to a limited extent into what's going on under the hood in DeepSpeed. DeepSpeed is basically a framework that allows you to train PyTorch-based deep learning models really, really efficiently, even if you're using a single GPU, but it makes the process of scaling to multi-GPUs and multi-nodes just amazingly easy. They do use a whole bunch of tricks and kind of, I want to say shortcuts, but that sounds like it's negative. They're not shortcuts. It doesn't, it trains your model just as well as any other framework, but it does it amazingly well. DeepSpeed's dead easy to use. The API for wrapping your PyTorch models into DeepSpeed is like, it's a 5-minute job. And the installation, they've got a pip install. The one thing I would say about DeepSpeed, other than you must check it out, I mean, my new approach is if I'm using PyTorch, I need a good reason not to use DeepSpeed as the engine to train my PyTorch models. I tend to use this install command here. I don't know why, but on my Ubuntu system, the pip install DeepSpeed doesn't work. They've got this alternative install command for Linux that just basically checks for some of your dependencies and then will install DeepSpeed in a way that works around them. The other thing to say about DeepSpeed is getting it working on Windows, ironically, given it's a Microsoft framework, is quite a challenge. I imagine, though, most people who are doing anything AI are probably using a Linux file system rather than Windows. This I don't want to dwell on. This was my bedtime reading last night, and I had the tab open this morning, so I thought I'd leave it there. This is from Microsoft. This is about the next steps that DeepSpeed is going to be taking. Again, some fantastic technology that is allowing us. Moore's law has kind of come to an end in terms of strictly silicon-based compute, but we're succeeding in pushing Moore's law with a lot of stuff that Nvidia are doing, and Microsoft are making a big contribution with some of this stuff around DeepSpeed and zero infinity. If you are particularly technically minded and you like to know about what great tricks are going under the hood to make deep learning training really, really efficient at scale, have a look at this. Microsoft are finding ways to squeeze huge models into GPUs that by rights should be too small. And so we're continuing to push that exponential computing capacity to keep up with what's happening in the deep learning space. And if you read this paper, you'll find that, trillion plus parameter models are very, very much on the roadmap for the cutting edge of what's happening, particularly in the NLP space. Right, coming to the end now. I don't like to talk for more than half an hour because people tend to stop paying attention, and I'm at 33 minutes, so I'll whip over this last bit. Just to say that, again, I've talked a lot about stuff that is most relevant at the high end of AI deployment. When you're looking at scaling out your deployment to sort of large data sets, high power clusters, multi GPU, multi-node environments. And again, just to reiterate the fact, it might seem like a nice problem to have at the stage when you're just having ideas at a hackathon, but it's well worth being aware of what it looks like at that end of the deployment spectrum, so that you can be ready for it. To that end, if you're using PyTorch and you're thinking you want to set up your code to be able to use multi-GPUs and multi-nodes, PyTorch is worth using DDP, distributed data parallel, rather than DP. DDP just works better at scale. That's just a little sort of side note there. Horovod, this came out of Uber. Again, Horovod, as with almost everything I showed you today, completely open source. Horovod works really nicely as a framework to training at scale, so it's one to think about reaching for. There are, of course, many other frameworks that allow you to train at scale, but these are just two I've seen being successful recently. And then finally, last thing I want to talk about is deployment or running inference. Now, for sure, no, you'd be doing amazingly well if you were actually thinking about running inference as a hackathon, inference as a service during the course of this hackathon. But I just want to flag this because at the start of your journey, it's worth being aware of what the end looks like. Once you've trained your deep learning model, of course, you want to run inference, and you want to have a really efficient pipeline for running inference. Because at that point, of course, your model is going to run super fast on a GPU. As we all know, running inference is much, much faster than training a model. So your whole pipeline needs to be super optimized to provide a meaningful service. I've already talked to you about the Clara Train SDK, just to flag the fact that Clara Train, which is Nvidia's medical imaging training platform, there is also a Clara Deploy. And this is a framework that, as the name would suggest, allows you to deploy your imaging models. And it's got full pipelines that are super, super optimized. It uses all sorts of tricks, such as parallel data loading and smart caching and all these highly technical tricks, right from the point where you've got your DICOM file sitting on disk to the point where you're returning the output of a deep learning model. It is built to scale across multiple nodes. It is built to use the latest Nvidia technology, so things like automatic mixed precision, the hardware accelerated sparsity, which we have on our latest Ampere cards. Clara Deploy will leverage all those tips and tricks to give you a really, really nice inference experience. There's also we have moving away from imaging specific stuff. The Nvidia Triton inference server is just a generic inference server where you put your deep learning model in here to run inference, and again, it will use all the sort of super deep level, CUDA level tricks available, and it will make the most of your hardware acceleration on your GPU to run inference really nicely. TensorRT is the framework that sits under the Triton server. Again, you probably won't want to use it during the hackathon, but just worth being aware that this thing exists, and if you want to run inference really, really fast because you're thinking about going to market, reach for TensorRT. Dead easy pipeline for getting TensorFlow models converted to TensorRT. PyTorch, it's pretty easy, but there are a few hiccups that we're kind of working out at the moment. Generally, with PyTorch, you want to kind of go PyTorch to Onyx to TensorRT. And then the final things I want to say, and I will stop screen sharing now. Again, one last time, I will drop my links into the Discord chat. This has been a very, very technical talk. I appreciate that. I thought about going for the clinical talk, but the fact is I haven't laid eyes on all the projects that teams are doing, so it's quite hard to speak from a clinician's perspective until I know exactly what people are trying. General pointers, From my perspective as a medic with quite a technical background, when you're making AI models, think about transparency. Clinicians are, we are a very suspicious, cynical, skeptical bunch, right? And we hate black box tools because at the end of the day, it's our patients' well-being on the line. It's our licenses and livelihoods on the line. If AI tools make a bad decision and there's a black box effect, so I'm not in the loop, I can't sanity check why that decision was made, that's a big problem for me. In radiology and computer vision, there tend to be nice ways of giving an intuitive sense. So you know, when you segment out a lung tumor, that's a really nice. I can immediately look at that and say, okay, the deep learning model thinks there's a lung tumor here, and it's drawn a line around it. There's a nice trick you can do where you can basically measure the Euclidean distance between the encoding vectors of two scans. So if I find a scan where I think there's a lung cancer, and I've got another scan somewhere in my repository where I know there's a lung cancer because that's been absolutely proven, and I search the encoding vectors of those two scans and find that they match really closely, what I can do is I can show a clinician, here's a CT scan where I think there's a lung cancer, and for comparison, here's a CT scan where there definitely is a lung cancer. And then the clinician can look at the two and say, yeah, I agree, they do look the same. Little tips and tricks like that work beautifully, particularly in the computer vision space. In other AI spaces, particularly around NLP, it's much harder to work out how you're going to achieve transparency, but that is a big challenge for technologists that we need to address in order to get these tools adopted and bringing benefit to patients in the clinical space. Finally, be careful how you present your findings. Now, I'm an associate editor of a journal called Intelligence-Based Medicine, and I do a lot of reviewing papers for that journal and a number of others. What you can often find is that projects that have been run by guys who are purely technologists and don't have a clinical background, the findings can be presented in ways that kind of, you know, they get you back up a little bit as a clinician. You know, people can train a deep learning model and it'll be a complete black box, and they'll say, oh, this is going to change the future of medicine and it's going to have a massive impact on medics. And you're sort of sitting there thinking, well, actually, for me, it's one piece of a massive puzzle that is a patient with an illness. We take into account loads of different data, we balance them against each other, and it's a human at the end of the day that is responsible for making a decision. Think about that when you're framing your projects, when it comes to the videos and the presentations. But also, and one of the challenges of the hackathon in track 1 is specifically about that. Also, think about how, you know, when you put the output of your application into the hands of a doctor or clinician in the medical space, really try and be aware of how they're going to use that and meet their needs. And don't just focus on getting a great AUC for your deep learning model. You know, usability is almost worth sacrificing some accuracy for, particularly if that usability is based upon transparency. I'd rather have a slightly less accurate model where I'm completely comfortable that I can interrogate its decision-making process. I would rather have that than a fantastically accurate model that has a complete black box effect, and I do not know why it's making the decisions it's making. That's a personal opinion. That is me done talking. That's 40 minutes, so I'm 10 minutes over my usual self-imposed time frame. Goran and Magnus, I'll hand back to you at this point.
Thank you, Rob, for a great presentation. I'm totally dizzy right now about all the possibilities you have with Nvidia solutions.
Good.
Yeah.
But I'm not a hacker.
That's what we want, right?
I'm not a hacker.
Thanks. It was great insights and great tips for the participants. I hope they found it interesting and that they will listen to advices. And this is it for today's stream. So just to wrap it up, and once again, to repeat myself, project page needs to be created today, and you need to add team members and write which track challenge you work on. You need to click submit, and you can edit the submission all the way to the end, so don't worry about it. Just submission will be visible to you and to us, so we know who is in the team and which track challenge you work on. So that's it. Thank you very much. And
thank you, Rob.
Again, thanks, Rob.
And thanks to the audience for watching. Bye.
Bye.
Thanks, guys.